that thing of equal value in its place, even if they don't look anything alike. Elimination, think about the word eliminate, means to get rid of. So what we're going to do, this method is also in other books called the linear combination method. So what we're going to do, we want to be able to add these two equations together in such a way that we can eliminate one of the variables. Now this first equation is already set up for that, because if I add this together, and I would encourage you, when you see that lack of coefficient, to put in 1, or if it's a negative sign in front, like here, remind you it's like minus 1q. Oops, and I really don't want to kind of almost cross off that, so minus 1q. When I add this equation together now, 1x plus 1x is 2x, and because the positive 7y, negative 7y, those are opposites, positive 7y minus 7y is 0, so we've eliminated y, and then 13 plus 5 is 18. Then when I divide both sides by 2, I get x equals 9. Remind yourself that you are not done. Your final answer needs to be the ordered pair, such that if I graph these two lines, I'm saying this is the point of intersection. If x is 9, I'm going to go back, and I think the first equation looks easier to plug 9 into and solve for y. I say that just because there's no minus in it anywhere. So I'm going to go back to my first equation. 9 plus 7y equals 13. When I subtract 9 from both sides, I get 7y, and positive 7y, paying attention to what's in front of it, equals 4. And then when I divide both sides by 7, if you put 4 divided by 7 in your calculator, you get a long decimal that fills up the whole screen. So you need to give this as a reduced fraction instead. And 4 over 7 is just 4/7 and can't be reduced. So y is 4/7. Now to do my check, at a minimum, I'm going to take my calculator, use the second equation, because the first one's what I used here. Use the other equation to double check this. 9 minus 7 times 4/7. Make sure it really does equal 5. So plug this side into your calculator, it equals 5, so this thing checks. Now I don't want to just add the next two together, because if I do, don't do this, I have to erase it in just a second. I get 7p, positive 3q minus 1q makes this plus 2q equals 18 plus 11 is 29. Yes, that is totally true. When I find the point of intersection, if I put p and q in here, this will check. Unfortunately, I didn't eliminate a variable. So if I need to eliminate a variable, what I need to do first is to create opposites. Here, I already saw the positive 7y, negative 7y. But 2p and 5p aren't opposites, because when I add them together, I don't get 0. And 3q and negative 1q aren't opposites, because when I add them together, I don't get 0. But what I notice is if this is positive 3q, if I just multiplied this second equation by 3, it would make this negative 3q, and then I would have my opposites. Now I'm going to erase this because I'm not adding them together yet. So the first equation, I'm just going to rewrite. 2p plus 3q equals 18. And then multiply everything in this equation by 3. Every single thing in that equation by 3. If you need to do the little bloopy things, do it. 3 times 5p is 15p. 3 times negative 1q is going to make this a minus 3q equals, and here's what people forget, 3 times 11 is 33. So a lot of people forget to multiply everything in that equation. Now when I add these together, I get 17p. This drops out because it's 0, equals 51. Dividing both sides by 17 gets me p equals 3. Now, we don't have x and y, but alphabetically p comes before q, so it's 3 something. I look again, I would choose probably the first equation because everything's positives. So 2 times 3 instead of 2 times p plus 3q equals 18. So 6 plus 3q equals 18. When I subtract 6 from both sides, I get 3q equals 12. And when I divide both sides by 3, I get q equals 4. That's a weird looking q. I think this is right. To check my answer, I didn't use the second equation just now. To check my answer, I do 5 times 3 minus 1 times 4 and see if that really does equal 11. It does. So This checks. Again, I look at this and I don't see opposites. I have two choices. Well, I have more than two choices, but two fairly obvious choices. I could say 2 and 7 both go into 14. So if I multiply the first equation by 7, I'd get a positive 14x. So to make the second equation negative 14x, I'd have to multiply by a negative 2. I'm going to choose not to do that one. You certainly could, and there's nothing wrong with it. I'm going to say, you know what? There are already opposite signs on the 4 and 3, so then I wouldn't have to multiply anything by a negative. If I multiply the first equation by positive 3, it's going to make this a positive 12y. If I multiply the second equation by positive 4, it's going to make this a negative 12y. Then I don't have to distribute a negative through everything. So when I distribute the 3, I get 6x plus 12y equals 120. And when I distribute the 4, I get 28x minus 12y equals 16. Now when I combine them, I'm going to eliminate y, and I'm going to have 34x equals 136. Then when I divide both sides by 34, x is going to equal 4. Again, I'm not done, or something. It looks to me, again, I would use the first equation just because everything's positive. 2 times 4 plus 4y equals 40. So 8 plus 4y equals 40. Subtracting 8 from both sides gives me 4y equals 32. Dividing both sides by 4 gives me y equals 8. To check my answer, I'm going to check it in the other equation, the one I didn't just use. So is 7 times 4 minus 3 times 8 equal to 4? Yes, it is. Now, we looked at those special cases in graphs. If I graph two lines, they might be parallel. Or if I graph two lines, it might be the same line. In substitution, you saw that the parallel ones, the no solution problems, you might got something like 6 equals 6 at the end. Or if it was that was negative 6 equals 6, because they're never equal, no solution. Or if it was infinitely many solutions, it was like 20 equals 20, two things that are always equal to each other. So there are infinitely many solutions. The same kind of thing is going to happen here. Again, I don't have opposites because if I add these together, I don't eliminate any of my variables. But what I notice is 5 goes into 10. So if this is already a negative 10x, if I multiply the first equation by 2, I'm going to have a positive 10x. So 10x plus 6y equals 20 is what I changed the first equation to. When I add these together, though, x is eliminated and y is eliminated. So this entire side is just 0. And negative 12 plus 20 is 8. 0 never equals 8. So 0 never equals 8 is my thought process. So my answer is no solution, which means if I graph those two lines, they are parallel because they never have a point in common. They never intersect. Here, again, I don't have opposites, but what I notice is, oops, I don't want to lose that negative. 3 goes into 6. Since this is a positive 6x, I'm going to multiply this by 2 to make this a negative 6x. And I'm going to get negative 6x plus 8y equals negative 14. Now the difference between that and the previous one, yes, everything on the left is eliminated and I get 0, but 14 minus 14 is also 0 on the right. And since 0 always equals itself, this ends up being infinitely, which is infinitely, many solutions. Now go ahead and pause this, try the last problem by yourself, and then come back and look at the way I solved it, which might not be the same way you did. We should get the same answer though. I do not have opposites. The thing that draws my attention is that 3 goes into 6. So since this is a positive 6y, I'd have to multiply the first equation by negative 2 to make this a negative 6y. Now you could have multiplied the first equation by 3 to make this a 6x, and the second equation by negative 2 to make this a negative 6x, and then combine things and it would be perfectly fine. But negative 2 times 2x, so this is going to become negative 4x plus 6y equals negative 18. And I just messed up. It's negative 2 should make it minus 6y. I add these together and I get negative 1x. The y is eliminated, equals negative 11. And then when I divide both sides by negative 1, x equals positive 11. So I'm going to go back to my first equation because it looks easier. 2 times 11 plus 3y equals 9. So 22 plus 3y equals 9. Subtracting 22 from both sides gives me 3y equals negative 13. Now, when I divide both sides by 3, I get a decimal that goes on forever. So I need to convert that to a fraction, and I end up with, and a mixed number in this case, negative 4 and 1/3. So y is negative 4 and 1/3. My check, again, use the equation I didn't just use. Check if 3 times 11 plus 6 times negative 4 and 1/3 really does equal 7. Plug this in your calculator. It does, so that checks.